Lecture 6.7, Spherical Mirrors. The formation of images from spherical mirrors follows the same flowchart of lenses, except for a few modifications. So let's set this up. So I'm going to set up a flowchart. So if I start to look at this guy, it's going to flow something like this. I think this is a little bit too big for me. And then I'm going to continue to go here. So now we could start at it. So what's the core? The law that describes everything that has to do with mirrors. It's the law of reflection. That's at the core. Then, in order to produce any images, you have three essential ingredients, just like we did with lenses. The first thing that we need is that we need a mirror's focal length. Let's call that F, of course. 2, we need an object is a distance S. And then finally 3, an image is created. Image is at distance S prime. So now I need to look at what creates this image formation. And we saw that with lenses, we had the basic language here. So let's go look at that. So the basic language is that in order to have image formation, we needed we started with ray diagrams. The language I used when I was young was tracing. Then we had a focal length. So the focal length of mirror turns out to be that it's 1/2 the radius of curvature. And then we have what I'll call a mirror equation. And that mirror equation is equal to 1 over f equals to 1 over s plus 1 over s prime. And then finally, we had a magnification equation. And there was two pieces. One, the magnification was equal to minus s prime over s. And then the magnitude of the magnification was the image height over the object height. As you can see here, there is a pretty good connection with lenses here. So the big difference here is really the focal length of the mirror and the ray diagram. And that's what we're going to focus on. So if I start to look at this process, and if I look at the overview of the mirrors, we then see here is that one, we have mirror characteristics. And because these are different than lenses, that's something that we have to cover. However, but if you look at the equations, the fact that the equations are the same, we see here that these image characteristics will be identical. So image characteristics are the same as lenses. So I'm not going to cover that. What will be different, besides the mirror characteristics, is going to be the ray diagrams. So that's something that I need to cover. And then finally, when you get to the mirror and magnification equations, are the same as lenses. So what we really got to deal with here is that we got to talk about this guy right here, mirror characteristics, and we got to deal with ray diagrams. So I won't cover 2 and 4. So let's get to that. So here we go. So now the first thing I'm going to deal with is I'm going to deal with mirror characteristics. And what we should start with is, what is a mirror? When I think of when you think of about a mirror here, here's what you should be thinking about. One, you have a piece of glass. Okay, here's a glass. And now in the back of the mirror, what you're going to do here is that you're going to put a coating in the back. And a lot of times in modern days here, they put in a thin coat of aluminum. In the old days, they used to put silver. So this guy right here is glass. And so what happens here is that when light comes in, you're going to find that, so if this is the incident light, what you're going to find here is that 99% of incident light. You know what? I should be a little bit more careful. What I should say is that 99.9% of incident light is reflected by the aluminum. So we're going to assume that that's 100%. So mirrors are governed by the law of reflection to produce images. And we could look at this. We could say that, for example, to see your feet in a mirror, and in this case, this will be a plane mirror, light reflects off the mirror and into your eyes. So if I create, let's say that this is you standing here. Okay, and then here's your eye. And you're standing right here. And then here's your shoes right there. So if I have a mirror, by the way, I don't need a full-length mirror, but I'm drawing one right here. Right? And there's my aluminum backing. What you're going to see here is that according to the law of reflection here, I can take the image point of my eye, okay, and this is the image. I don't want to say the image. I should say that this is my eye behind the mirror. So I can now draw a ray from my feet to the eye, So if I go from here to here, and then you could see I'm just doing this type of thing. Then this guy is then going to go straight into my eye right there. So if I draw a normal here, let's say that this is my normal to the mirror right there. That didn't go so well. How about if I draw my normal from here to here? This angle and that angle are exactly the same. So therefore, the law of reflection tells us that these two angles, how about if I put a prime on one of them, have to be identical. That's what I mean when the law of reflection occurs here. So now what I'm going to do here is that even plane mirrors are considered part of spherical mirrors. We will deal with spherical mirrors. And which means here is that we're going to have a converging mirror, a diverging mirror, and we're going to have a plane mirror, a flat mirror. Those are the three possibilities. So what I'm going to do here is that I'm going to create a sphere, and then I'll just modify it. So I'm going to create a circle here. And how about if I make it this big? So now I just got to make a circle out of this. And what I'm going to do here is I'm going to make this thick. So that's going to be my mirror right there. So when I look at this, oh, that's not what I wanted. So when I look at this smear, what you're seeing here is that this smear is then, you could imagine that this guy here is a hollow sphere. And what we're going to do here is you could see here is that this point, which is the center of the lens, has a radius of curvature r, and the center of the sphere is typically labeled C, which is the center of curvature, and r is called the radius of curvature. So C here is called the center of curvature. R is called the radius of curvature. Now, here's what we'll do here, is that now we're going to sort of slice this guy up a bit. So now if I have an aluminum, so now what I'm going to do here is that I'm going to erase some of this. And you could imagine that I come in and I erase, let's say, this amount. And then I'm going to come over here and I'm going to erase this amount. So what you're seeing here is that I now have two pieces of the thing here. So now this is what I'm going to do. Now, let's say that I put backing right here. Right? So here's my backing. So in other words, this right here is my aluminum backing. And so this piece right here, this is the reflecting surface. Maybe I should put this over here. So if I look at this blue part here and this blue part here, this is the reflecting surface. And then I'm going to put backing right here as well. And so what we say here is that this piece right here, this is what they call a concave mirror or a converging mirror. This guy right here, this is a convex or a diverging mirror. Now, if I make the radius of curvature infinitely large, then I get a flat plane mirror. So now let's look at a piece of these guys here. So the first thing I'm going to deal with is that I'm going to deal with a converging mirror. So because it's commonly called a concave, I'll write concave to remind you, but I'm going to stick to the word converging mirror. Now, I have a converging mirror right here. So what I'm going to do here is that I'm going to copy this right here. and then I'll just modify it. So very similar to a converging lens, a converging mirror takes parallel light, reflects it, and converges the rays on the same side of the light source. To a focal point. So let me put in this little piece here. And again, I will modify this thing. So now what I'm going to do here is that I'm going to draw my my central optic axis. So I could imagine that I have my central axis that goes something like this. And what we're going to find here is that if you look at the radius of curvature here, this guy was 1, 2, 3, 3.5 squares. So then I'm going to go, and I'm going to move this thing so that it's right in the middle of this thing. So then I'm going to go 3 squares. So I'm going to go 1, 2, 3. So right here is the center of curvature. Okay. This is the center of curvature right here. By definition, the focal length is half of the center of curvature. So then that means here that this has to be about right here. This is the focal point. So if I look at our definitions here, we could then say, we know that C is the center of curvature. So then F here is our focal point. And then we have our focal length. Now, it turns out that the focal length of a converging mirror is exactly 1/2 the radius of curvature, and it has a plus sign. So now I could then say that this guy from here to here is now the focal length of a converging mirror. So you know what? So I'm just going to say that I'm actually not going to write that. So now let's draw our rays here. So our rays are now going to do this. I'm going to have rays coming in. They're incident. And then what they're going to do here is like they're going to reflect through the focal point. And they're going to move like this. And so where they cross, that's what our focal point looks. But let's just be a little bit careful here. So the law of reflection says that if I pick the normal, then that angle and that angle have to be the same. If this is my normal, then this angle and that angle are the same. So instead of drawing a curved surface, we want to do the same thing that we did before. We want to use a line to describe the mirror. So what I'm going to do here is that I'm going to create a line, and I'm going to take this and I'm going to make it a thick line. And this is what I'm going to do here. So I'm going to take this guy. Now, apparently I didn't do this right. I'm going to take this and I'm going to, this is going to be my converging mirror. So what I'll do here is that to change this a little bit, I'm going to add little corner pieces like this here. And you could see that that kind of tells you what actually happens here. So instead of drawing this curved mirror, I'm going to draw this mirror instead and call this a positive focal length. So then if I look at this guy and I do the exact same thing, then when I think of a mirror, and this, let's say that this is my focal point right here, then I'm going to have rays that come in. They come in, they reflect. And I now know that when they reflect, the incident and reflected angles are exactly the same. And so when I'm looking at this guy here, these guys will reflect like this as well. And now you're seeing that this point now tells me that I now know that this here is the focal length. And look what I set up here. What I set up here, it's on the same side as the light source. So now that I got that, I could then go on to the diverging mirror and do the exact same thing. So if I look at the diverging mirror, this is what they call a convex mirror. And before I go on, I'm going to come up and I'm going to take this piece with me because this will be useful. So now let's go look at a diverging mirror. So a diverging mirror, we could then say that a diverging mirror does the opposite of a converging mirror. So here, instead of converging the light, it diverges rays away. However, following the rays with our eyes, they appear to cross behind the mirror. And that's exactly what happened with a diverging lens. that is the diverging mirror, the diverging mirror's focal point is on the opposite side, not the same side, the opposite side of the light source. So let's look at this thing again. So if I paste the piece that I just copied, now let's go look at this thing. So if I look at this guy, what I'm looking at is that I'm looking at the front side of this guy. And so what I'm seeing here is that once again, this is going to be, let's say that this is the center of curvature. When I start to draw my central line, my central axis, you're going to see here that half of this, which will be about right here, this guy is the focal point. And so very similar to what I did up here, note that I looked at rays coming in. So I'm going to look at rays again. And so if I look at these rays coming in, they come in here. And what happens here is that they diverge. So the way they diverge is that they appear that they're coming from the focal point behind the mirror. So in other words, if I follow them back, they appear to be right there. They appear to emanate from this point, but they clearly diverge. So if I look at these rays, again, the law of reflection tells me that this angle and that angle, this angle and that angle must be the same. So that being said, we could then come in and we could now simplify this diagram using, again, a thick line. So let's get this thick line. And here we go. So the way I'll do this here is that I'm going to do this here. I'm going to draw a thick line. Let's say I draw it right here. So what will be different in this case here is that you saw that these guys curved inwards for the converging to follow that. For a diverging, I'm going to say that they curve outward like this. And as a consequence, this here is a negative. So now if I start to look at what actually in this new picture, then I'm going to say, let's say that this is my focal point right here. So now if I have my rays coming in, and I follow this, they're going to look something like this. And so the focal length is then the distance from here to here, but that focal length is negative. So if I now look at the focal length of a diverging mirror, is then going to be minus 1/2 r, which is the radius of curvature. So that is the details of these mirrors. So I have a positive focal length for converging. I have a negative for a diverging. So now let's keep moving along the same directions. And just to repeat the exact same thing here, I'm going to say here is that because lenses and mirrors have the exact same mathematical equations. Mainly, I'll say that this is the mirror equation now instead of the thin lens equation. Some people call it the lens, what do they call it? They call it the image object equation. And the magnification equation I'm not going to cover them, right? I will not go through these details. However, the sign conventions are opposite of lenses. And I really can't answer why, but let me give you some insight as to probably why you would think that they would be different. Okay, so the question is, it goes something like this. So for lenses, the vast amount of light from the object goes through the lens. So if I have my lens right here, and let's say here's my lens. Oops, that's not what I wanted. So if this is my lens right here, then when I look at my central axis, what we're finding here is that on this side is the object, and the light is moving in this direction like that, from left to right. So what we're saying here is that on this side, we say that this is where, so we say that most light passes through. And because of that, we call this the positive side. Not really sure what happened over here. Let me try that again. On the other hand, we could say that on this side, over here, we could say that almost no light is here. And they identified this as the negative side. Now, I could say the exact same thing for mirrors. On the other hand, for mirrors, all of the light gets reflected. So picture-wise, it's just the opposite. So let's say here is that this is, in this situation, I now have a mirror instead of a lens. So when I look at this thing, what we're seeing here, that in this situation, the light, of course, is coming from this direction, and this is here is where the object is at. And so we then say here is that we can say here is that all light is reflected. And because all light is reflected, we then define this as the positive side. And on the other hand, we say here that there is no light is here. And so we call this the negative side. So in essence, to keep the same optical equations, and what I mean by that is I mean that 1 over f is equal to 1 over s plus 1 over s prime, and m equal to minus s prime over s. To keep the same optical equations with the same signs to match the lenses convention, the mirror sign convention is opposite. Now, the wording is a little bit funky here. Now, I shouldn't have put a, and what I mean here is that to keep what we mean by an image as being, if I have a positive image distance, then that means I have an erect real image. If I have a negative image distance, then I'm going to have an erect virtual image. So When I say this same sign convention, I really mean that if S prime is positive, then I know I have an inverted real image. And if I have something that's negative, then this is going to be an erect virtual image. So when I say the same signs to match the lens convention, that's what I mean by that. So then if I just highlight this thing, then this is what we're going to have. The only way to do this here is that if I have an object distance now, so, or the object location, I should probably say, we define this as S, is always positive. So again, if I pick my sign convention, then this side right here, this tells me on this side that if I have an object here, in this case, let's say that this here's my object right here. This object will always be positive on the left side. So we then say that the object, we call this a real object on the left side. Now, if I look at images, then if I look at image location, which is S prime, can be positive or negative. So now if I look at, let's say that I have my mirror right here. So then if I start to look at what I'm on both sides of the mirror, then I'm talking about I have two sides here. So on one side, I look at the side of the object. So over here, I have my object. And then clearly, I have a second side over here. So if I have an image that lands on the same side as the object, then that's positive. So this gives me positive values. If it lands on the other side, then that's negative. So I get negative values behind the mirror. So if I have positive values, as we've seen already, then this has to be inverted and real images. On this side, we're going to have erect and virtual images. And then the sizes varies. On the left, I could have smaller, same, or larger size images. And on the right, I could have smaller and larger images, depending on whether I have a converging or diverging lens here, or mirror. So let's go look at the ray diagram, or this situation here.